of a circle is decreasing at a rate of 7.2 feet per second. At the instant the radius has a length of 11 feet, answer the following. A. At what rate in feet per second is the radius changing? So first we need to find the derivative of the radius, dr over dt, knowing the formula for the circumference of a circle and the area of a circle when the radius is 11 feet. So, to do this, you're going to take the circumference of a circle and take the derivative of it, which would be dc over dt equal to pi times dr dt, and plug in the rate of the circumference change. So negative 7.2 feet per second equals 2 pi times dr dt, and divide by 2 pi to leave you with dr dt, and using a calculator you would get negative 1.146 feet per second, and your statement would be the radius is decreasing at a rate of 1.146 feet per second when the radius is 11 feet. For part B, at what rate in feet squared per second is the area changing? You need to find the derivative of the area, dA over dt, when the radius is 11 feet. To do this, take the area of a circle, pi, or A equals pi r squared, and derive to get dA over dt equals pi times 2r times dr dt. Now, you found dr dt in part 1, and you can plug in to get dA over dt equals 2 pi times 11 feet times the negative 1.146 feet per second. And you combine the multiplication. Using a calculator you would get dA over dt equal to negative 79.2 feet squared per second, and your statement would be the area is decreasing at a rate of 79.2 feet squared per second when the radius is 11 feet. On a windy day, a demented history teacher goes outside to fly a kite. The wind is blowing at a brisk but constant 8 miles per hour, and the kite maintains an altitude of 125 feet. Calculate the following at the instant 340 feet of string has been released. For part A, we want to know the wind speed in feet per second. So, to do this, you're going to use a conversion table to convert 8 miles per hour, going from miles to feet and hour to minutes, to get 42,240 feet over 3,600 seconds, which simplifies into 176 over 15 feet per second. And for part B, we want to know the length of the string, or how fast is the length of the string increasing. So, in our picture, we want to know how fast, or the dc over dt, when c is equal to 340 feet. So to do this, we need to calculate side A, the bottom base of this triangle, and we know B because it's a constant altitude of 125 feet. So using the Pythagorean theorem, you plug in and take the squares and square root, which gives us A equal to 316.188. Now, we can find the rate. Plugging in, take the derivative of the Pythagorean theorem, plugging in the A value found, and using from part A, the dA over dC, and plugging in C value that you know, 340 feet. Go ahead and divide both sides by 680. Using calculator, you would find 10.912 feet per second is the rate increasing, and your statement would be the length of the string is increasing at a rate of 10.912 feet per second when the history teacher has let out 340 feet of string.
A man walks along a straight path at a speed of 3 feet per second. A searchlight is located on the ground 28 feet from the path and is kept focused on the man. When the man is 2 feet from the point on the path closest to the searchlight, determine the following. Part A says, how far is the man from the searchlight? So first off, we want to pull out and define all important information and also define what our questions are asking us. For part A, we are trying to find C when B equals 2 feet. So if you look at our picture, we're trying to find the length here when B is 2 feet. To do this, we'll use the Pythagorean theorem, a squared plus b squared equals c squared. Plug in what we know, 28 squared plus 2 squared equals c squared. Add and raise to the exponents and take the square root, and you get that C is 28.071 feet. Now for B, it asks at what rate is the searchlight rotating. So to do this, we'll have to use theta, which is the angle in between the searchlight and the man, which is moving as the man is walking. To do this, we'll use our tangent theta equals b over 28. We'll take the derivative, which is secant squared theta times d theta over dt, and we'll plug in the rest of our information down here. It's going to be secant squared of theta, which is 0.071, which we calculated over here. That is tangent of theta over 2 over equals 2 over 28. And when we do the inverse tangent, we get theta as 0.071. And then we're going to multiply it by the derivative of theta and set it equal to the other half of our equation, which is the quotient rule from b over 28. When we use our calculator to define this, it equals 0.107. So secant squared is the same thing as 1 over cosine of the same theta times d theta over dt equals the same right side. When we calculate this with our calculator and multiply across, we get d theta over dt equals 0.107 feet per second. So our statement for finding side C would be the distance between the man and the searchlight is 28.071 feet when the man is 2 feet from the point on the path closest to the searchlight. And our written statement for part B, where we found the change in theta, is the searchlight is rotating at a rate of 0.107 feet per second when the man is 2 feet from the point on the path closest to the searchlight.